In episode 29, titled Sampling Strategies, Stratification, Oversampling, and Class Balance, the goal is to choose sampling strategies that protect minority outcomes, because many DataX classification scenarios involve rare events where naive sampling produces impressive-looking accuracy and dangerously poor detection. Class imbalance is not just a modeling inconvenience. It changes what metrics mean, it changes how probability outputs behave, and it changes what kinds of errors your system will make if you are not deliberate. The exam rewards you when you can see imbalance in the prompt, choose a sampling strategy that fits the objective and constraints, and avoid leakage mistakes that inflate performance. This episode will define stratification, oversampling, and undersampling in plain language, then connect them to evaluation fairness, calibration, and governance. You will also practice the idea that sampling is not only a technical step, but a policy decision, because it affects whether you prioritize misses or false alarms. By the end, you should be able to defend a sampling strategy in scenario language without drifting into tool-specific detail. The point is to make your sampling choices consistent, safe, and aligned with the exam's expectation of disciplined evaluation. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Stratification is sampling or splitting in a way that preserves group proportions, meaning the fraction of each class or group in your sample reflects the fraction in the population you are trying to represent. In practice, stratified splits are most commonly used when dividing data into training and evaluation sets, ensuring that both sets contain a representative share of the minority class. This matters because if the minority class is rare, a random split can accidentally create an evaluation set with too few positives to measure performance reliably, or a training set that barely contains the signal you need to learn. The exam often tests this through scenarios where outcomes are rare and evaluation must be fair, and stratified splitting is the safe, defensible choice. Stratification can also apply to sampling across subgroups, such as ensuring representation of key segments, which supports fairness and generalizability. The key is that stratification preserves reality rather than reshaping it, which makes it especially important for evaluation integrity. DataX rewards stratification reasoning because it shows you care about representative measurement, not just model training convenience. Oversampling is intentionally increasing the representation of the rare class, usually by duplicating minority examples or generating additional minority-like examples, so the learning algorithm sees enough positive cases to learn useful patterns. This is a training-focused technique that addresses the problem that many models will otherwise optimize for the majority class and treat the minority class as noise. Oversampling can help a model pay attention to rare events, improving recall or sensitivity, but it can also increase the risk of overfitting if you simply repeat the same rare examples too many times. The exam expects you to treat oversampling as a tool, not as a default, and to apply it in a way that respects evaluation integrity. Oversampling is often most useful when the minority class is so rare that the model does not have enough examples to learn stable patterns, and when collecting more positive examples is not immediately feasible. DataX rewards understanding oversampling because it connects directly to rare event detection, which is a common exam theme. The key is to oversample responsibly and only in the training context after proper splitting. Undersampling reduces the majority class to balance learning by removing some majority examples, creating a more balanced training dataset. This can be useful when the majority class is enormous and repetitive, and when training on all majority examples is computationally expensive or leads the model to ignore the minority class. The cost of undersampling is that you throw away information from the majority class, which can reduce the model's understanding of the full variety of normal cases and can increase false positives if the model does not see enough legitimate variation. The exam may frame this as a trade between computational feasibility and representation, where undersampling can be a pragmatic choice when resources are limited. Undersampling is often paired with careful evaluation because you want to ensure that reducing the majority class does not create a distorted view of normal behavior. DataX rewards learners who recognize that undersampling can help training, but can also harm precision if normal variability is underrepresented. When you choose undersampling, you should be able to articulate why the lost majority information is acceptable in the scenario. Class imbalance affects accuracy and probability calibration, which is why sampling strategy choices ripple into evaluation and operational policy. Accuracy can look excellent in imbalanced data even when the model misses most positives because the majority class dominates the count of correct predictions. Calibration, which is whether predicted probabilities reflect true event rates, can also be distorted by imbalance and by sampling, because the training distribution may not match the real-world prevalence. If you oversample the minority class during training, the model may learn a different base rate than reality unless you correct for it through calibration or threshold setting. The exam often tests this by presenting a model that looks good in development but produces unexpected alert volumes in production, which can be caused by prevalence differences and calibration issues. Recognizing that sampling changes the training distribution helps you avoid assuming that probability outputs are automatically meaningful in the original population. DataX rewards this because it shows you understand that training convenience can create deployment surprises if not managed carefully. When you connect imbalance to accuracy traps and calibration shifts, your sampling decisions become more defensible. Selecting a sampling method should be driven by cost and data availability, because the safest solution is often to collect more minority examples when you can. If positives are rare but collecting more is feasible, improving data coverage may be better than aggressive resampling because it adds real diversity rather than repeated or synthetic examples. If collecting more positives is slow or expensive, oversampling can be a practical bridge, especially when you need to train a model that can at least recognize the minority class. If compute is constrained and the majority class is huge, undersampling can help training efficiency, but it must be balanced against the risk of losing important normal variation. The exam may describe tight deadlines, limited labeling budgets, or limited storage, and the best sampling choice will respect those constraints while protecting detection ability. This is where you make a professional decision about what limitation is dominant, whether it is lack of minority examples, excessive majority volume, or evaluation reliability. DataX rewards the learner who chooses the sampling strategy that addresses the true limiting factor, rather than applying a one-size approach. When you can explain your choice in terms of constraints and learning needs, you will score well. Stratified splits are a foundational safety measure because they keep evaluation fair across classes, especially when the minority class is rare. If your evaluation set has too few minority examples, performance metrics like recall and precision become unstable and can mislead you into thinking a model is better or worse than it truly is. Stratification during splitting ensures that each partition contains a proportional representation of classes, which makes evaluation more reliable and makes comparisons between models more meaningful.
The exam often rewards stratified splitting because it is a best practice that prevents accidental class disappearance in a partition.
Stratified splitting also helps when you are evaluating across subgroups because it ensures that important segments are represented in both training and evaluation.
This supports fairness analysis because you cannot measure performance differences across groups if one group is absent or underrepresented.
DataX rewards this because it aligns with governance and validation integrity, which are recurring themes. When you see rare outcomes and evaluation requirements, stratified splitting should be one of your first instincts.
A critical rule is to avoid oversampling before splitting, because doing so causes leakage risk by allowing duplicates or synthetic variants of the same minority examples to appear in both training and evaluation sets. If the same underlying case is present in both sets, the model can effectively memorize it, producing evaluation scores that are artificially high. This is a classic exam trap because the sequence mistake is subtle and very common in practice. The safe sequence is to split the dataset first, preserving evaluation integrity, and then apply oversampling only within the training partition. That way, the evaluation set remains a clean representation of unseen data, and performance metrics remain meaningful. The exam may describe a pipeline that oversamples and then splits, and the correct answer is to identify leakage risk and correct the sequence. DataX rewards this because it shows you understand evaluation hygiene and how easy it is to fool yourself with contaminated splits. When you remember that oversampling must occur after splitting, you avoid one of the easiest ways to inflate performance falsely.
Synthetic approaches like SMOT, which stands for Synthetic Minority Oversampling Technique, can be appropriate when creating additional minority examples helps the model learn a more general decision boundary. SMOTE generates new minority-like points by interpolating between existing minority cases in feature space, which can reduce overfitting compared to simply duplicating cases.
The exam may mention synthetic oversampling, or may ask which technique helps create additional minority examples without exact duplicates, and SMOTE is a common correct answer in that framing.
However, synthetic sampling must be used carefully because it can generate unrealistic cases if feature relationships are complex or if the minority class has discrete or constrained values. It also must be applied only within the training partition to avoid leakage and to maintain evaluation integrity. DataX rewards this nuance because it shows you understand both the benefit and the risk of synthetic examples. When you mention SMART, the defensible reasoning is that it can help learning when minority examples are scarce, but it requires careful application and validation. Distribution shifts over time can undo sampling assumptions, which is why sampling strategy must be paired with monitoring and periodic review. If the prevalence of the minority class changes in production, metrics like precision can shift, even if the model's discrimination ability remains stable, and thresholds may need adjustment. If the nature of the minority class changes, such as new fraud patterns or new failure modes, oversampling historical positives may become less helpful because it reflects old patterns. The exam may describe performance degrading or alert volumes changing over time, and the correct reasoning often includes considering drift and base rate shifts. Sampling strategies that were appropriate during development may no longer match the operational environment, especially if the training distribution was reshaped through oversampling. DataX rewards the learner who recognizes that sampling is not set and forget because real-world systems evolve. When you connect sampling assumptions to monitoring and drift, you are thinking about the full life cycle, which the exam consistently rewards.
Sampling choice should also align with business priority, specifically whether misses or false alarms are more costly, because sampling influences what a model learns and what trade-offs it can manage. If missing positives is catastrophic, you may lean towards strategies that improve recall, such as oversampling, while accepting that precision may suffer and planning for triage. If false alarms overwhelm operations, you may be more cautious about aggressive oversampling and may focus on calibration, thresholding, and preserving majority variation to protect precision. The exam often frames this as fraud versus safety versus churn, each with different cost structures, and sampling choices should reflect those consequences. This is also where you remember that sampling affects probability calibration, which influences how thresholds behave under changing base rates. DataX rewards this alignment because it shows you are choosing a strategy for a reason tied to harm and capacity, not simply applying a known technique. When you can explain how the business priority guides sampling and threshold policy, your answer becomes coherent and defensible. Documenting sampling in model carts supports governance and reproducibility, and the exam may explicitly reward answers that include this kind of accountability. A model card is a standardized description of how a model was trained, evaluated, and intended to be used, including key decisions like sampling strategy. Sampling affects performance, fairness, and calibration, so it must be recorded so future reviewers can interpret metrics correctly and reproduce results. Documentation should note whether stratified splitting was used, whether oversampling or undersampling was applied, what method was used for synthetic sampling, if any, and how evaluation was kept clean. It should also record the target prevalence in production, because sampling can change training prevalence and create deployment surprises if not understood. The exam rewards this because it aligns with responsible model management, where decisions must be defensible and auditable. When you mention documentation, you signal that you understand that sampling is not just a technical choice, but a governance-relevant decision that affects real outcomes. A reliable anchor is to remember split first, then sample, then train safely, because it captures the sequence discipline that prevents leakage and protects evaluation integrity. Splitting first ensures your evaluation set remains a clean proxy for unseen data. Sampling second, within training only, ensures you reshape learning without contaminating evaluation. Training last ensures the model learns from the intended distribution while still being judged fairly on the original distribution. Under exam pressure, this anchor prevents a common mistake that can inflate performance and lead to wrong choices in multiple-choice questions. It also gives you a simple way to justify your pipeline order when asked about best practices. DataX rewards this because sequence discipline is a recurring theme across evaluation, thresholding, and pre-processing. When you apply this anchor, your sampling decisions become safer and your evaluation conclusions become more trustworthy. To conclude episode 29, choose a sampling strategy for one scenario and explain why, using the scenario's prevalence, costs, and constraints as your guide. Start by naming whether the positive class is rare and whether missing positives or generating false alarms is more costly in that environment. Then, state that you would use stratified splitting to preserve class representation in evaluation because that protects fair measurement. Next, choose oversampling, undersampling, or a combination based on whether you need more minority signal, need training efficiency, or need to preserve majority diversity for precision. And mention that oversampling must occur after splitting to avoid leakage. If synthetic oversampling is appropriate, justify it as a way to improve minority representation without exact duplicates while still validating realism. Finally, state that you would monitor prevalence shifts and document the sampling strategy for governance because sampling assumptions can drift over time. If you can narrate that reasoning clearly, you will handle DataX questions about stratification, oversampling, and class balance with calm, correct judgment. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.